Okay, get this. What if I told you that to make an AI smarter, you first have to teach it how to forget? I know, it sounds completely backward, right? But it's actually one of the most powerful ideas in all of modern AI. And today we're going to break down exactly how it works.
So let's just start with this one big question. What if the biggest problem in making a truly smart AI wasn't that it learned too little, but that it actually learned too well? I mean, what if it got so good at memorizing every single tiny, irrelevant detail that it completely lost the ability to see the bigger picture?
Well, that question right there leads us straight to the villain of our story today. It's a classic problem in machine learning, and it's called overfitting. Think about it like this. Imagine a student who's cramming for a huge exam, but instead of learning the concepts, they just memorize the exact answers to every practice question. Now, they might totally ace a test if it uses those exact questions, but you give them a brand new problem, one that needs real understanding, they're completely lost. That, right there, is overfitting. The AI has basically just memorized the training data, noise, quirks, and all, but it hasn't actually learned the principles behind it. Okay, so how in the world do you solve a problem where an AI learns too perfectly? Well, back in 2014, the legendary Geoffrey Hinton and his team came up with a solution that was so elegant and honestly so shockingly simple. They called it Dropout. Yep, that's it. That's the whole idea in a nutshell. While the AI is in the middle of learning, you just randomly turn off parts of its brain. I know, it sounds like you're actively trying to sabotage it, but it turns out this is the secret to building a much more robust, much smarter AI. In this team analogy you see here, it is the absolute perfect way to get your head around this. If you have one superstar player who always scores all the points, what happens? The rest of the team gets lazy, right? They never really learn to contribute, they just become totally dependent. But if you make that star player sit out of practice every now and then, you force everyone else to step up. They have to develop new skills, learn to work together differently, and guess what? The whole team gets stronger. That is exactly what Dropout does inside an AI's neural network.
So how does this actually work under the hood? Let's get into the mechanics. It's actually a pretty simple process, but it's one that repeats over and over again, thousands of times during training.
All right, so with every little chunk of training data that comes in, the network just randomly shuts down a fraction of its own neurons. Poof, they're gone, for now. Then it trains on this new, smaller, temporary version of itself. But for the very next batch of data, it resets everything and then drops out a totally different random set of neurons. This happens constantly, over and over, keeping the network in this state of perpetual change. Now, here is the absolute key thing to remember. This whole process of randomly turning neurons off, it only happens during the training phase. When it's actually time for the AI to do its job, to classify an image or translate a sentence for you, Dropout is turned completely off. The full, complete network with all of its now much stronger and more versatile neurons is brought online to make that final prediction. Okay, so all this constant shuffling and changing, it builds up to something incredibly powerful. You see, the real magic of Dropout isn't just that it stops neurons from getting lazy. It's about what it creates. It's this incredible phenomenon called the ensemble effect. Yeah, let's go back to our basketball team. Dropout basically forces every single neuron to learn how to pull its own weight. Think about it. Since any of its neighbors could just vanish at any given moment during training, a neuron simply can't afford to rely on just one pathway for information. It's forced to learn robust, independent features all on its own. And what you get is a much, much more resilient system overall. And this is where the true power of Dropout really clicks. Every single time a new set of neurons is dropped, you're basically training a slightly different, smaller neural network. So by the end of it all, you haven't really trained just one giant network. What you've actually done is trained a massive collection of them, all at once. And the scale of this is, well, it's just staggering. I mean, look at this. If a layer has n neurons that can be dropped, you're essentially sampling from 2 to the power of n different possible mini-networks. Even with just a handful of neurons, that number becomes exponentially, mind-bogglingly huge. It's kind of like you're averaging the opinions of thousands and thousands of different experts, but you're doing it all super efficiently inside just one training process. Okay, so this all sounds great in theory, but where do we actually see this stuff? The answer? Pretty much everywhere in the AI you use every day. Seriously, from the AI that automatically tags your friends in photos,
to the powerful language models behind chatbots and translation apps, all the way to the systems that understand your voice commands. Dropout is a fundamental bedrock tool that's used to make all of these models more accurate and more reliable, especially when they face brand new data out in the real world, like, say, a doctor using AI to analyze an MRI scan it's never seen before.
But, like any powerful tool, Dropout isn't some kind of magic silver bullet. It's really important to have a balanced view of where it works best and where it doesn't.
So, on the plus side, it's fantastic at crushing overfitting, and it's surprisingly simple to actually implement. But on the other hand, all that randomness means training can sometimes take a bit longer. Plus, it adds another knob you have to tune, that dropout rate. And honestly, for really small networks, you might not even need it at all.
And that rate, which is usually just called P, is absolutely critical. How many neurons should you actually turn off? If you do too few, you won't get the real benefit. But if you do too many, the poor network might struggle to learn anything at all. A good rule of thumb is to start at about 50% for the main layers and then tweak it from there. It's a perfect example of the art that goes into building these amazing AI models.
So, what's the big takeaway here? We started with this crazy, simple idea: let's just randomly break an AI's brain while it's trying to learn. But where we ended up is with this really profound principle that by preventing things from getting too specialized, by forcing them to adapt, you actually create a stronger, more resilient system in the end. And that leaves us with a pretty fascinating final question to chew on. If forcing a little bit of imperfection makes AI stronger, where else might that